Okay, so we are going to move on. So I'll just talk through this note, and you have a sheet to fill in while I am talking. So you can fill in the sheet as I go, listening and pausing, and I also will upload the PowerPoint for you. So just so you get used to the way I discuss the eye brain, I will be using a picture of the eye. Now, as I said before, it is actually your brain that sees. That is where it takes all those signals that come from your eyes and changes them to actually thoughts and vision. So what we see is processed in our brain, which again is why optical illusions work so well, which don't worry, I will be sending some your way. So meet your eye brain. So these are, these little eyes with feet are going to be your observers on diagrams often during this unit. So we're going to be showing the light either entering the eye or not entering the eye, but do know we call it the eye brain because it's actually your brain that does the seeing. So here we will start. And again, you're going to need to pause this and fill in the blanks. If you miss something, just go back. So when we look at something that emits light or a source of light, so whether it be the sun, in this case, we're going to be using a candle. So the source of light or this candle, it emits light in straight lines in all directions. Um, and so we only can see the light that actually enters our eye and then is perceived by our brain. We do not see the light that doesn't enter our eyes. So there's this light you know, all around us that we're not seeing that light. We're only seeing the light that enters our eyes in a straight line from the source, or as you're going to see, is reflected off of something and then has a straight line into our actual eye. So we do not see light that is directed away from our eyes unless it is reflected into our eye brain by something. So here, if we look at this specific light ray, it obviously that light ray would not enter our eye. However, if there's something that it interacts with, in this case it's a droplet of water, that will cause the ray to be reflected or bounce off of it into our eye, then we can actually see that light ray. So most of our vision is actually occurs from light bouncing off of objects around us and into our eyes, which is why at night in the dark we can't see anything. We're still surrounded by the same objects, but there's no light bouncing off them and into our eyes. We can't see them. So on diagrams in this unit, we will tend to ignore all light that does not enter our eye brain. So we're going to be doing things called ray diagrams, where we're showing the rays of light coming from the light source, bouncing off of whatever and going into our eyes. We're really only concerned with the ones that are going to get into our eyes. So we're really not going to be concerned with all these other ones. They're there. We're just not going to acknowledge them because we're only concerned with the ones that enter our eyes and cause us to see things. So to simplify, here's what that diagram above, we're not going to draw all the arrows of light that are emitted. We're just going to show only the rays that are emitted and go into our eyes. And do note that when we draw light rays, we must put a direction on them. So they have to have a direction, which is an arrow. People love to leave the direction off their light rays. We have to show it, okay? So I'm just starting you out now. And if you haven't got yourself, a protractor and a ruler, so important to have a ruler because we need to have straight lines for this unit. So start thinking about getting those things. So nice straight line coming from the light source directly into our eyes, arrow showing direction. So the path light takes is called a ray. Okay, so that's important. Diagrams that show how light moves from the object to the eye are called ray diagrams. Do note you should be looking at that worksheet that you need to fill out as I go here and stopping when you think, you've got something to fill in there. You won't be uploading this worksheet. I know this worksheet shows that it's out of a certain amount. You're not going to be uploading this one. I just want you to get the information. So light is a type of energy that our eyes are sensitive to. So remember, there's all kinds of energy all around us. We looked at the electromagnetic radiation spectrum, and there's the gamma rays, the microwaves, the radio waves. There's waves all around us. This is the type of energy that our eyes, which is actually our brain, is sensitive to. So it's the visible spectrum of light. So this is called an operational definition because it only tells us how we detect light, but it does not tell us what light is. Can you see the eye, brain's feet? Well, here's an example. Can this person here, eyes are right here, see this figure's feet? Okay, well, we're going to answer that in a minute. So light travels in straight lines. This is called rectilinear propagation. You may need that. Since no ray of light can go straight from the eye, brain's feet into your eyes, you can't see them. So literally, I know his feet, do watch, his feet are not a source of light. But should light be reflecting off of them, let's say because it's daytime or even nighttime and we have lights on, you still wouldn't be able to see the eye, brain's feet. Oh, for goodness sakes, cat, shush! Oh my God, my cat wants in my room. She's just relentless today. So he can't see her feet because there's just no straight line path that goes directly to this person's eyes. Okay, so this is where you need your rulers because you have to be able to draw straight line paths from what we want that individual to see. And if there is no straight line path, then they can't see it. So in this case, no, he couldn't see the eye, brain's feet. Experience has trained our eye brain to expect that things are located in the direction that the light comes from. So what would we see? In this instance, this is what it would look like. This is what this person would see. Okay? Would not see feet, would just see the eye. Okay, so if we look, where does a straight line go? Well, it goes from below the eye. We can draw a straight line from below the eye into his eyes and above the eye. So he would just see this part of the eye and no more. Okay? Newton was the first to note that white light breaks into colors of a rainbow when it passes through a prism. And I love to use my prism in class and white light and break it into a rainbow, but we're not going to do that. You're just going to have to trust me on this. We already covered what this visible spectrum of light is. If you recall, Roy G. Biv. There used to actually be a color between blue and violet called indigo, and they've taken that out. It was kind of a bluey purple color. So all white light can be divided up into this spectrum. When light from the sun, or white light, is broken down, its spectrum looks like this. And there we have Roy G. Biv. And do note, those colors of light are actually energy that we can see. It's the only energy we can see. We can see that energy. Infrared, so before red, in this direction, if you remember, on the electromagnetic spectrum, if we go in this direction before red, we can feel infrared, but we cannot see it. How does it feel? It feels warm. Okay. And of course, if we go in this direction, we'll get to ultraviolet. And again, we can't see that. So these are all different wavelengths of energy. White light is made up of shades of red, orange, yellow, green, blue, and violet. The mnemonic, sorry for remembering the order of rainbow colors, is the name Roy G. Biv. So, when light from sources is broken down, its spectrum looks like a series of lines. All spectrum can be further separated until they appear as a series of lines. The above line spectrum is from light coming from an iron heated until it gives off light. Most light sources are made up of many different colors. Newton noted that the colored lines could not be separated further. So, these lines are pure colors and are identified by a frequency and wavelength number. So, here's a conceptual definition, which gives us a better understanding of what light is. So, the atoms in sources that produce light are surrounded by electrons that can be excited to higher energy levels. As electrons fall back to their original energy level, they give off the energy in the form of light. So excited electrons, so energy in, and then they fall back down and they release that energy in the form of light. That is a pretty complex thing that you're going to cover both chemistry, actually it's covered in chemistry, physics, and biology, believe it or not, is that concept of energy being released when excited electrons drop down in energy level. So that's a grade 12 concept, so we'll fly by. Hopefully in grade 9 you did a lab where you took different elements and you used the Bunsen burners and you lit those elements on fire and you heated them up, excited their electrons, and when they drop back down, you got different colors for the different elements. That's just a fun lab to do. And again, I would have done it with you this year if you didn't do it, but unfortunately, here we are looking at pictures of colors of light being emitted when the electrons drop back down. So depending on what level you started in, when they drop down, the electrons will produce different colors. So it totally depends on where the electrons started and where it dropped down to. That will give you different colors. Not nearly as fun as the Bunsen burners, but it is what it is. So the conceptual definition of light, you're going to need this one. The conceptual definition, that's not what I wanted to do. I'll undo that. The conceptual definition, here it is, of light is: light is produced when electrons change energy levels. So there are many ways for atoms to gain energy. For instance, incandescence is the emission of light from a body due to its temperature. The atom gains energy by being heated. So adding heat will cause the electrons to jump out in energy level and then drop back down. So our ears cannot hear some high sound frequencies that dogs can. And in fact, because I'm older, I cannot hear some frequencies that you guys can as teenagers. And I know I used to love, there was some app in your phones that you could play sounds that I couldn't hear, but you guys could. And they were these like really high pitched sounds. And yeah, that was always fun. People getting that app out and seeing who could hear and who couldn't. I could never hear it. My ears are not great. And in a similar way, our eyes cannot see some of the colors of light. So there's colors that we can't see. We're not capable of. As I said, infrared, which is on this side of, oh no. Let me get this in black here. Here we go. So infrared, yeah, snakes can see that. So that's the one that comes before red. And ultraviolet after violet, right? And that's, if you were an insect, you could see that one. So, for instance, you cannot see if an iron is hot or not. Our